Hello everyone, myself Dr. Reena Devi, Assistant Professor, Department of Physics, XLM College, Vellore. In this video, I am going to explain about the Laue's equations in condensed matter physics. For this case, first we consider a crystal plane. Everyone knows that a crystal contains a large number of atoms that should be arranged in a regular and a repeated manner. So the Laue illustrate that the X-rays scattered from different atoms and combine to form a diffraction beam and provides a Bragg's equation. So in this diagram, you could see S naught be the two parallel incident beams which is scattered by the two identical scattering centers A and B is nothing but that atoms in a crystal planes, and that should be separated by a distance r. And scattered beam is to be deflected at a very long distance away. So we can derive the path difference between the two parallel planes. Let us now calculate the path difference between BP and AQ with the help of two triangles, that is a triangle BPA and the triangle BQA. Already we know that S0 and S be the unit vectors along the direction of incident beam and scattered beam respectively. For the first triangle BPA, cos theta will be equal to adjacent side by hypotenuse, therefore BP by AB or BP by R. So from this BP is equal to R into cos theta. So R is nothing but a distance between the two parallel planes, and the cos theta will be equal to the incident beam, that is S0. In a similar manner, the next triangle BQA, from this triangle AQ will be equal to R into cos theta, or AQ is equal to R into S. Here S is nothing but the scattered beam. Therefore, the path difference BP minus AQ will be equal to S naught into R minus S into R. We can take S R as a common term, and therefore S naught minus S into R. And AQ and BQ are the projection of R, and the vector S naught minus S be the direction normal to the two parallel planes. In this screen, the second diagram shows the combination of the two triangles, which consists of both incident and scattered beam, makes an angle of 2 theta, and the distance will be modulus of S naught minus S. Suppose we are going to take the first half of the triangles, which is represented by modulus of S naught minus S divided by 2. So for the first triangle, we can calculate the sin theta will be equal to modulus of S naught minus S divided by 2 and the whole divided by modulus of S. And already we know that modulus of S will be the unit vector, therefore sin theta will be equal to modulus of S naught minus S divided by 2, or the modulus of S naught minus S will be equal to 2 sin theta only. Now we can use the vector formula, that is modulus of A minus B is equal to square root of A square plus B square minus 2AB cos theta. So in the place of A and B, we have to use S naught and S, that is the incident and scattered beam, and modulus of S naught minus S is equal to square root of modulus of S naught square plus S square minus 2 S naught into S cos theta. But I already know that S naught and S will be the unit vector, so we can substitute, which is equal to 1. So finally we may getting a square root of 2 into 1 minus cos theta, and 1 minus cos theta will be equal to 2 into sin square theta by 2. So here 2 will be getting cancelled if you are taking square root. So finally we will get 2 into sin theta. In order to determine the phase difference between the parallel planes, we will use a formula from Bragg's treatments, that is pi p is equal to 2 pi by lambda into path difference. Already we determined the path difference is S naught minus S into R. Hence we can substitute the above equation as shown in equation 2. For the condition of diffraction maxima, the phase difference between the atoms A and B be an integral multiple of 2 pi, but this condition is satisfied only in the nearest neighboring atoms, which are separated by primitive translation distances A, B and C. Here replacing R by ABC, and equation 2 becomes 2 pi by lambda into S naught minus S into A is equal to 2 pi H prime, which is equal to 2 pi nh, and 2 pi by lambda S naught minus S into b is equal to 2 pi k prime is equal to 2 pi into nk, and 2 pi by lambda into s naught minus s into c is equal to 2 pi L prime, which is equal to 2 pi n into L. That is equation number 3. Here h prime, k prime and L prime may be the three integers, and considering as a common factor, that is h prime will be equal to nh, k prime is equal to nk and L prime is equal to nl. It forms the smallest set of integers which is identical to the Miller indices. Next, we will move on to the angle between the parallel planes. In the beginning itself, I have said that S naught vector minus x vector be the scattering normal. Let us consider that alpha, beta and gamma is the angle between the scattering normal and ABC or the crystal axis respectively. Therefore, the following equations are S naught minus S into A is equal to 2A sin theta into cos alpha, S naught minus S into B is equal to 2B sin theta cos beta, and S naught minus S into C is equal to 2C sin theta into cos gamma. This is equation 4. Now we can substitute equations 4 in 3. We will get 2 pi by lambda into 2A sin theta cos alpha is equal to nh 2 pi. So in this above equations 2 pi will be getting cancelled. Then finally 2A sin theta cos alpha is equal to nh lambda, and 2B sin theta cos beta is equal to nk lambda, and 2C sin theta cos gamma is equal to nl lambda. So this is equation 5. So these equations are known as the Laue's equations. So from the Laue's equation, that is equation 5, we notice that the direction cosines of the normal to HKL planes are proportional to h by a, k by b and L by c. Therefore, we conclude that the scattering normal S naught minus S vector is identical to normal HKL planes. That is, HKL planes may be regarded as a reflecting planes, and Laue's equation provides the validity of Bragg's treatment. Let us now consider D be the spacing between the two adjacent planes of HKL family. Therefore, D is equal to A by H into cos alpha, which is equal to B by K into cos beta, and C by L into cos gamma. The above equations have been obtained from a crystal structure in a cubic D spacing, that is 1 by D square is equal to H square plus K square plus L square divided by A square plus B square plus C square. Therefore, after substituting all these values in equation 5, finally we will get 2d sin theta is equal to n lambda, that is nothing but a Bragg's equation, and here n is the order of the diffraction. So finally we conclude that Laue's equations provides a validity of Bragg's statement. Thank you.